I wanted to type learning. Thanks for the introduction. Yeah, as you see, what I want to choose. First I'd like to thank the organizers for holding this great conference here. And the topic I want to talk about is mapping class of services. And basically what I wanted to do is to learn, to study possibilities to learn mapping class from their finite quotient actions. But since I noticed this conference, I mean, there is a topic in the conference that the volume conjecture. So I try to connect it with a certain topological version of of volume conjecture. I guess this conjecture has already been mentioned in on the first day's talk. This is, in general, people are concerned about, suppose you're given, in general, you can try to ask if you can pass through finite cover and then, no. Right. For example, this could be like like this might imply that for some irregular tower of cover, this right-hand side is greater than epsilon, something like that. Right. So if you look into that conjecture, you may ask some soft questions. So suppose I wanted to approach this conjecture and I might want to start with some more special cases, then what kind of assumptions can I impose on it so that it helps? Well, if you just look at the conjecture itself, it could be really a hard question. But you can first try to relate it to some other conjectures or questions that have been attracting interests. For example, one of them is what's called the profinite or profinite rigidity. It's related to, for three manifolds, it's related to the fundamental group. It asks if you look at, suppose you want to study a three manifold group, but you don't have too much information about its topology, then maybe you want to try to look at all its finite covers. Then the question asks how much information about the three manifolds itself can be recovered just from the set of all the finite quotients. So sometimes it's denoted, the set of finite covers is denoted by C, sometimes called the genus of the group, and it can be translated in terms of profinite completions. So if you take this notation, then what I put here can precisely put like this. Suppose you're given an M, can you find a finite set of three manifolds so that whenever you have some three manifolds whose fundamental group has set of quotients equal to that of M, then that three manifold disappears in your finite list. So that's a question. You might you might feel like the most natural to ask. Suppose you have two manifolds. If they have the same profinite completion, do they have the same fundamental group? But there are some examples for which this does not hold. So the statement become a little more complicated. For those uniqueness, for those examples with uniqueness, then people just put profinite rigidity. And in general, if you talk about this finiteness, let's just say it's something called profinite almost rigidity. So how's this statement related to the torsion growth conjecture? It's not directly related, but at least it gives you some necessary conditions. Suppose for hyperbolic three manifold, if you assume the homological torsion growth conjecture, or if you believe in the torsion growth conjecture, then then I guess this profinite almost rigidity would follow from that conjecture. Well, this is easy to see because you remember on the left-hand side, the quantity is like the torsion part of the homology, or the homology of some finite cover. So that is something purely topological. You can just recover it on the fundamental group level by taking finite covers. So suppose 2, 3 manifolds have the same profinite completion of their fundamental group. You will, and if you assume this homological torsion growth conjecture, that will tell you that these 2 hyperbolic 3 manifolds have the same volume, and in that case, there is a classical result which tells you that with any given volume value, there are only finitely many hyperbolic 3 manifolds with volume exactly that value. So if you assume that that torsion growth result, you will get profinite almost rigidity for hyperbolic 3 manifolds, which means that this conjecture can be thought of as a necessary condition or a testing case for that conjecture. And in recent years, this profinite rigidity or profinite properties have attracted more and more attentions, partially because some more years ago people studied more about virtual properties, which means that you want to find, for example, you're given some 3 manifolds, you want to ask, okay, if I'm allowed to pass to some finite cover, can I get a finite cover with some desired property? For example, non-trivial torsion or fiberness, stuff like that. And then after that, some people, for example, Alan Ray and some of his co-authors noticed that probably it's more important to study the set of finite quotients of a fundamental group as a whole, and that set might give you more information about the topology of 3 manifold group. You're not looking for individual finite covers anymore. You're trying to put them together and try to extract information from that. Last 2 years, I guess there are some first examples. One is that for hyperbolic surface bound over a circle, you do have profinite rigidity, which means that they have a really strong statement. So it says that among all the finitely generated residually finite groups, if you see some group whose set of finite quotients coincides with hyperbolic surface bound over circle, then the group itself must be the fundamental group of that surface bundle. So it's pretty strong, and for Weeks manifolds they proved the same thing in last year. So it does give you some supports of this profinite rigidity for this conjecture, and the reason that we put it, we weaken the statement is basically because there are some known example which does not satisfy the strongest statement like rigidity itself, but it gives you some finiteness or finite possibilities. So one of the example is, I guess this is a very nice example, and if you keep that in mind, it will be good for this talk. So actually, several decades ago, Stipp found this pair of matrices, and this pair of matrices, they have a so believe me, they have determinant 1, and then you can notice that you can notice that they have the same trace, which means that they do have the same eigenvalues, or in other words, they must be conjugates in SL2C. You can prove stronger they are conjugating SL2Q. But it turns out that they're not conjugating SL2Z. What is interesting is that if you take any congruence quotients, you will notice that the quotient matrices just become conjugate to each other. So what it tells you is that if you translate in terms of into topology, it tells you that if you have two torus bundles whose monodromy are given by this pair of matrices, then these two torus bundles will have the same profinite completion fundamental groups, because those finite quotients are just characterized somehow by this second line, and the first line somehow tells you that their fundamental groups are not isomorphic. So this is basically why we cannot state for profinite rigidity for all three manifolds. There are some examples like this, and Funa actually generalized this set of examples to an infinite family. I guess his interest was to construct a certain three manifolds with the same Tareyev-Vero invariants for a certain spherical category, which I'm not expert of. But anyways, he has some other motivations which are somewhat connected to this, and he generalized these examples to an infinite family. Okay, so this is roughly the situation about profinite almost rigidity, you can say that, okay, this conjecture, if this conjecture holds true, then it supports the homological torsion growth conjecture in a certain way. But still, even this conjecture seems hard to me. And I want to, so for this talk, I want to step back a little more. And, okay. This page is trying to explain what the difficulty lies in. If you think about how to approach this profinite almost rigidity, then, for example, the first thing you want to try to extract out of it is like the simplicial volume, and you want to maybe try to rid of something more. But well, when you pass to finite quotients, then how do you do that? I mean, for general three manifolds, I would say this still looks difficult to me. But what I want to do is just take one more step back, and we look at even simpler situation. We look at mapping classes of a given surface. You can translate it into the case of surface bundles with some slightly more restrictions. So this becomes this main topic of my talk. So I wanted to consider a similar situation. Suppose you're given a surface, and you take two mapping classes in the mapping class group. Then you can try to consider some similar situation. Suppose these two mapping class, well, any mapping class just induces outer automorphisms on any quotient by characteristic group. So you can consider, if you take any finite index characteristic subgroup of the fundamental group, then you can try to consider the induced action or induced outer action of these mapping classes on the finite quotients. And we say, I made up some words, and we say that they are procongruently conjugates if they just induce the conjugate outer actions on any characteristic finite index quotients. This line is just a definition of profinite conjugacy, and similar like the situation of profinite completions, you can organize this this definition in the first line in a more group theoretical way. You can say that you consider the automorphism of the profinite completion of the fundamental group. Then procongruent conjugacy says that two mapping clauses are just conjugate to each other in the outer automorphism of the profinite completion. Okay, this is just some notion. The perspective that we take is something like this. Suppose we're given two mapping classes. I would think they act in the same way on the surface if they are conjugate to each other in the mapping class group, because you're sort of just looking at the surface in another way than you see the other mapping class. Right. And the formulation about this procongruent conjugacy follows the same way. You just speak of things on the finite quotient level and talk about the outer automorphisms, and you still want them to want the relation to be just a conjugacy between mapping classes. That's sort of the suitable analog to the isomorphism of profinite completion for three manifold groups. Okay. Any questions about this formulation here? Because I'm gonna move on from this point. Right. So what I wanted to say is that if you consider this similar situation, but you just talk about this procongruent conjugacy relation on mapping classes of three manifold of surface groups, then what you can get is a statement like this. If for any mapping class, then at procongruent conjugacy class, just so for any mapping class, the procongruent conjugacy class is made up of finite conjugacy class and mapping classes. So if we want to put it in plain words, it basically says that surface mapping classes are almost determined by their finite quotient actions. That's what I wanted to. That's a point that I wanted to make for this talk. I guess. Right. So for the rest of the talk, what I wanted to say is not try to sketch the whole idea for proving this theorem, but we sort of look at special situation, which is sort of the most interesting, is that you just consider pseudo-annals of maps. Remember that in the case of three manifolds, I said that if you look at profinite completion of the fundamental group, it's really hard to extract any topological or geometrical invariants out of the finite quotients. But in the case of mapping classes, or procongruent conjugacy of mapping classes, the situation is slightly better because there is one important invariant that you can read off from this procongruent conjugacy class. That is the stretching factor. And I'm talking about pseudo-annals of maps. And similar to the situation of finite volumes three manifolds, if for pseudo-annals of maps, if the stretching factor is given, then there are only finitely many conjugacy classes of mapping classes with that stretching factor value. So it will give you some, at least, it will give you some immediate consequence, procongruent almost rigidity for pseudo-annals of mapping classes, something like this. Is that if you have one of the mapping classes pseudo-anorthogonal, and in any other mapping class that is procongruent conjugate to F would also be pseudo-anorthogonal, and they must have the same mapping. They must have the same stretching factor. Starting that's what this theorem tells you. And starting from here, you can invoke some well-known results by Arnold-Yocos and Ivanov that tells you stretching factor determines mapping class up to finite conjugate, up to finite possibilities. Again, if you think about this, there are still, Steve's examples are still there, and it just tells you that if you just consider torus bundles over a circle or mapping classes of a torus, then you won't be able to get uniqueness for statements like this. For example, in general, you are not able to replace this finitely many as with the word unique. But still, for pseudo-anorthogonal examples, there are no known examples where things are not unique. So we're still interested in the question. So if you just think about pseudo-anorthogonal maps for hyperbolic type surfaces, then do we have a uniqueness for some surfaces like this? I guess all of you have seen pseudo-anorthogonal, the definition of pseudo-anorthogonal maps in certain cases, but I still want to say a word about, just remind you the definition. When I entered this morning, I noticed that there are some nice pictures that I want to make use of. So we talk about when we talk about pseudo-anorthogonal map, then you want to say that when you have a surface automorphism, by saying F is pseudo-anorthogonal, that means you will have two transverse families of foliations that are invariant under the action of the automorphism, and there are some. Actually, you get something more than a foliation. You get a measured foliation, which means that there are some transverse measure which tells you how thick leaves are. So you get, for example, ignore these black lines.
You should have told me.
Oh, you are the author? Cool. That's great. So let's look at this blue line. This blue line forms one form of foliations, and this red lines follow another family of foliation, and this displays a singularity, a prone singularity of over 3. Because you have 3 singular leaves going out of surface. And basically, pseudo-anorthogonal map should preserve this foliation, but for one family, it should stretch the measure by some constant lambda, which is called the stretching factor. And for the other foliation, it would rescale the transverse measure by 1 over lambda, so that in total it preserves the area, but for one direction it's stretched, in the other direction becomes thinner. By the way, this is a nice picture. Okay, so that give you some basic idea of pseudo-anorthogonal maps. It has some well-known connection with three-manifold topology. When you have pseudo-anorthogonal maps, and if you look at the mapping torus of that map, then equivalent you can characterize by saying that, okay, the mapping torus has a hyperbolic geometry on it, or it admits a hyperbolic structure in the sense of certain. So pseudo-anorthogonal corresponds to hyperbolic in three-manifold world, if you know the Nielsen-Thurston classification of surface decompositions, then the reduced type just corresponds to non-geometric case for the surface for the mapping torus, which is surface bundle. And there is another type called periodic that corresponds to the product geometry, hyperbolic by Euclidean on 3 manifolds on the surface bundle. So there are some dictionary that helps you translate between surface mapping classes and surface bundles over a circle. You can go back and forth. So I guess in the rest of the talk, I guess in the rest of the talk, I want to try to sketch some idea to prove this theorem. This for the pseudo-Anosov case. How is it possible to rid off the stretching factor from this all the finite quotient actions? But before doing that, I wanted to mention one example, which is, for one thing, it's a very nice example, and for the other thing, it tells you that some very naive way does not work. For example, if you're given a pseudo-Anosov surface automorphism, I guess the most natural way to approach the theorem would be that I'll try to pass to some finite cover. For example, I might start with some element in the Torelli group, so I don't see this stretching factor just by looking at its induced homological action. But I can ask, okay, suppose I'm allowed to pass to some finite cover and try to lift the automorphism to the finite cover. So I do have some chance to get some new eigenvalues, which might fall out of the unit circle. Will I be able to find some finite cover so that some eigenvalue that I get out of this way is just a stretching factor? I mean, this is a very, very natural way to approach, and there are some examples where you can pass the finite cover and get the stretching factor out of that. But what I mentioned here, this is a pretty surprising result of Macmillan, which said that, okay, whether or not you can make a virtual homological eigenvalue the stretching factor depends on the intrinsic topology of the mapping class itself. If your mapping class, if you look at this invariant foliation associated to your pseudo-Anosov map, suppose all the singularities are even order singularities, then just by some simple topological construction, you will be able to find some two-sheet cover of the surface, and there will be a stretching factor. There will be a homological eigenvalue there, which equals the stretching factor. In other words, you can try to find some two-sheet cover so that the foliations are transversely orientable. Okay, but suppose you're not so lucky. If you have some prime singularity of odd order, then Macmillan proved that you will not be able to recover stretching factor out of homological eigenvalue. And he actually proved something stronger. It says that there is a gap so that you cannot get this lambda out of a limiting process by taking, for example, the upper bound of all the possible virtual homological eigenvalues to recover this stretching factor. So if you keep his example in mind, you got to find some other way to do that. And you know what we know about this set of finite quotient actions. It's actually more than some single value on each level. So we want to try to use it more systematically. Yeah, this is a question. We want to try to just look at the set of all the finite quotient actions and find some strategy to recover those dynamics of the mapping class itself. So what do I mean by the dynamics of the mapping class? The most basic thing that I refer to are those, for example, fixed point indices, and the periodic point indices, and other quantities coming out of it, like Nielsen numbers and Lefschetz number, stuff like that. But before that, yeah, this is a quick answer to the question just now. So what we want to use is, first of all, we want to use a fixed point theory, because that's closely related to dynamics of the hyperbolic surface. And what we want to use in recent three-manifold topology is the conjugate separability for three-manifold groups. I'll try to tell you how to somehow combine these two ingredients to get the theorem. Let me first mention a further step of the dictionary I mentioned. I told you that mapping classes corresponds to surface bound over circle. Just by this simple construction, take you take these so-called mapping torus, and then on it there are various associated structures. One of the structures is just that if you flow along the real direction, then it just descends to a flow on the mapping torus called the suspension flow. And yeah, for pseudo-Anosov maps of the standard type, then the fixed point of f can be translated into those one periodic closed trajectories of the suspension flow, and those m periodic orbits are translated into m periodic closed trajectories. So you can go back and forth. The good thing about what's on the left is that these are just free homotopy classes of loops, so they can be represented by conjugacy class of the fundamental group. Okay, we'll use that further. And on the left-hand side, we're just talking about this standard form of pseudo-Anosov, so we can replace some more technical words with fixed points and periodic point orbits. And in general, in fixed point theory, it does not necessarily talk about fixed points, but they group fixed points into classes. So they do talk about fixed point classes, periodic orbit classes, and there is a notion of indices associated to these numbers. And for those with non-zero indices, those are called essential ones. So these are just some extra terminology that you want, you can make use of. So that's this is the connection between two-dimensional and three-dimensional. And the basic observation, eventually we want to get, eventually we want to get to stretching factor of the mapping class. And the way we do it is that we do know there is a limiting process that approaches stretching factor. We know this. If you take the number of m periodic orbits, its growth rate would approach this stretching factor. It's actually, you can take it as one of as a definition of the stretching factor. So you do know there is a limiting process, and suppose you can recover these Nielsen numbers, this m Nielsen numbers, then that tells you you will be able to recover stretching factor. So our task just becomes try to recover this number of m periodic orbits. using using induced finite quotient actions. And in general, if you have some experiences dealing with mapping classical review, there are some natural comparison that Nielsen number is sort of a number which is always positive, and it's greater than what is so-called the Lefschetz number. Lefschetz number is sort of the generalization of Lefschetz trace in the classical Lefschetz trace formula. And what I want to use is a certain twisted version of Lefschetz numbers for pseudo-analytic maps. You don't have to look into details of the formula, but I'll try to tell you what to look at. Basically speaking, you will start with some mapping class. Then you will try to choose you try to look at the representation of the fundamental group of the mapping torus. That will give you some representation, and you can speak of its characters. And then the set of m-periodic orbits also plays a role in this, which appears here. There is L that is periodic points corresponds to trajectories, so they can be so in this expression, what you get is first you look at some periodic orbit class, then you turn it into a closed trajectory, which is a conjugacy class of fundamental group. Then because the character is invariant over conjugacy classes, so you take the conjugacy class of any of the representative in that. That will give you some value. This is just a complex value in general. And you multiply it with the index, then summing up over all the m-periodic orbits. Then you get a topological invariant that depends only on f and rho, which is called the m-periodic. I should put Lefschetz number. Sorry. You will be able to recover. You will be able to express topological invariance in a nice way that closely associated to the dynamics of the manifolds. And if you know the Reidemeister torsion, and if you take log of that expression and expanding it in certain formal way, this number will just appear as coefficients of the formal power series in that. If you ignore this character part, you will just recover the classical Lefschetz number for the mapping class. And what we do here is that we just introduce some representation and twist the expression a little bit to get a more interesting invariant quantity. Okay, so our strategy is try to recover this Nielsen number out of this Lefschetz number, or at least we try to connect Nielsen numbers with these numbers. What is interesting to notice is that in this expression, when you vary this representation, these coefficients might vary, but this index, or which terms to appear, is something that does not vary. But you have a number of representations. So if you look at all the possible finite representation, perhaps you will be able to recover. You will be able to recover the number of terms inside here. That's a basic. That's a basic idea. I'm copying that expression. Question? So if you look at this expression here, you notice that this is a sum over all the periodic m periodic points, and this is something that might vary, but you know the number of characters that you have for any finite quotient equals exactly the number of conjugacy classes in gamma. So suppose you have some finite quotients so that every m periodic trajectory just becomes separated from each other in the quotient at the conjugacy class. Then for that kind of gamma, you will be able to you will be able to read all the finite representations and tell that okay, this sum is a sum of that number of terms. Okay, that will give you the size of this set. But the point is, the problem is that for general group work, in general you will not be able to find such nice finite quotients so that any conjugacy class upstairs become any different conjugacy class upstairs become different downstairs in some finite quotients. But this is a nice property that does hold for three manifold groups. There are some extra remarks that I was saying that okay, if you do this, if you look at these finite quotients, as m increases, you will be able to look at larger and larger finite quotients and use the Lefschetz numbers to recover this this Niel's number, because when for any fixed m, when you take large quotients and when the number of occupied periodic trajectory or occupied conjugate classes stabilizes, that number will equal exactly to the size of this set, which equals this Niel's number. So there is a connection between twisted Lefschetz numbers and the Niel's number, where three manifold topology come into as that for three manifold groups, we do know this conjugacy separability property for I guess I should put pi 1 of mf here. That tells you that suppose you have two different conjugate classes here, then you will always be able to find some finite quotient so that in the quotient the conjugacy classes are different in the quotients. This result is actually some new results. You do need to invoke the virtual specialization of three manifold groups, and the very statement comes from the fact that for right-angle arcing groups, you will be able to obtain conjugacy separability. Actually, Minassian introduced some stronger notion called hereditary conjugate separability, and this is proved for right-angle arcing groups. As an implication, I mean, you need to work harder. Like this is very deep work of Hamilton, Wilson, and Zaleski. But this is sort of one of the essential ingredients in their work. So if you take this conjugacy separability and combined with the observation that I mentioned in terms of fixed. Oh, I'm out of time. So well, with this what I mentioned before, then you will be able to almost recover the theorem about pseudo-Anosov maps that I mentioned. But there are some other things you need to say. You need to say that, for example, the Lefschetz numbers or the expression is invariant or is determined by the set of finite quotients. So there are some subtle things, technical things you need to check. You need to use twisted homology and twisted finite homology to prove for invariance. And well, this is just something appeared in the proof. And in order to prove the main result about finiteness for general mapping classes, you will need some more things. You will need this this result of Wilton-Zaleski, which tells you profinite completion determines the geometric decomposition. And then there are some subtle things associated to those decomposition tori that you want to look into. Combined with those things, you will be able to prove the general case. Okay, so I guess that's the end of my talk.
Any questions? If not, let's thank the speaker.